So this is lecture number 31 of EE 503. And in lecture number 30, in the last part, we have solved this example. So let's remind ourselves what this example is. Assume that we have a density which is flat in this region indicated by A. Okay. So that region is some part of XY plane. Okay. So you can see the three-dimensional plot over here. So in this region where the boundary points are again 1, -1 and -1, the height above this area A, let's say, is 1/2. Okay. So density is uniform over this area indicated by A. So what's the problem? Given this joint distribution of X and Y, if we only observe X, okay, if I only observe a point, something like this, then can I estimate the variable of interest, which is Y? So last time we have solved this example, and we have defined mean square error as our cost function, and we have seen that this estimator, which is psi of X, as you see over here, minimizes the mean square error. Okay, so what is this estimator? This estimator is calculating, a value from this given observation X, and it's mapping this X to, let's say, a Y hat value. Okay, so how do we get this? Well, for a given X value, let's say I'm over here, X observation, X naught, then this density is over this line, the conditional density is, again we are observing that it will be just a slice of this. Okay, and this slice will be area normalized, and then I will get this conditional density. So what is important is that this is again flat. Okay, so on top of this there is a flat, let's say, height. That height does not vary by Y position and so on. So the conditional mean of this density, meaning that this part, is our estimate. So as we have said last time, all of these mean square error, or let's say mean absolute error cost functions, some other cost functions, reduce to evaluation of posterior density. So what do I mean by the posterior density? Posterior density is this. Density of desired variable Y given your observation. Your observation is X. Okay. So how can I find the density of this? So if I can find the density, then we have seen that the mean value of this density will be, the mean value of this density is minimum mean square error estimate for Y. Okay. So you may say the median value. We haven't derived this, but median value. So this is the minimum mean absolute error estimate for Y. So what do I mean by mean absolute error? Actually, it is something like this. Expected value of this is desired value is Y. You are trying to estimate it from X, but this is just the magnitude or the absolute value of this error. Okay. So mean is this calculation, absolute is this calculation, and clearly error is this. Okay. So this is minimizing this time mean absolute error. So at the end, what do I get? From this posterior density, I extract a single parameter or single scalar value, mean value, let's say, then that becomes the minimum mean square error estimate. If I extract the median of this density, okay, then this becomes the mean absolute error, minimum mean absolute error estimate, and so on. Okay, last time we have covered this, maybe we haven't covered this part. So at the end of the last lecture, we have even calculated this minimum value, minimum mean square error value. Okay, so what does this mean? Among all functions, continuous, discontinuous, etc., all of those functions, this function is very special because when I insert this function over here and take the expectation over desired variable Y and observation X, because I have two random variables right now, joint distribution of X and Y, evaluate this, expectation over the joint distribution, then for this specific function, I get this minimum value, which is 1 over 12. Okay. So this lecture, let me discuss, okay, let's continue with this example. Let me give another proof. Another proof, this is a simpler proof actually, for mean square error value for the previous example. So this example. So I want to use the concept of orthogonality. Let me write it over here. Because this will be as you can imagine, we pay so much attention to this vector space concepts. So this will be coming into play over this minimum mean square error calculation. So what should I calculate? So min.MSE is this expected value of over y and x, y minus, well, let me write this, okay, let me indicate this optimal estimator by something else, let's say this, okay, psi of x, which is, this is the optimal estimator, 1 over 2 sine of x, okay. Now I should calculate this. So what should I do? Well, I should maybe write this expectation like this. Okay, I have something like that. So what's going on? So if you call this error, let's say epsilon, then I have epsilon squared over here. So this is epsilon times y minus epsilon times psi of x. Okay, with minus over here. Okay, so there is nothing much to do up to now. But this is the important part. Now I claim that this is equal to 0 without doing any operations. So how can I claim that one? Because please remember, this is the error. Let me write error of optimal MSE estimator. Okay, optimal MSE estimator realized by this psi function. That is that error. And this is nothing but, do you remember we were defining, let me use this color. For example, g of x, an arbitrary function of observation. So this is g of x is an arbitrary function of observations. If I have multiple observations, this will be x vector, but I have a single observation x over here. And we have proved that the orthogonality principle. So let me write it over here. Remember, expected value of y minus expected value of y given x, this is the estimate of y, this is the error, times g of x is equal to 0. This is what we call the orthogonality principle. Orthogonality, okay, for this MSE estimator. But this is valid for all g of x functions. G of x functions. Again, last time we have discussed this. So this is again optimal estimator, and this is an arbitrary function as we have said. Okay, so this is very remarkable if you think about this. This says that at the end of this estimation process, the error random variable, this is error random variable, this is the error random variable. So the optimal estimator creates an error random variable which is orthogonal to, let's say, x, orthogonal to x squared, orthogonal to x cubed, orthogonal to sine of x, orthogonal to tangent of x. This is very remarkable because it is basically saying that this optimal estimator extracts all dependencies from this all nonlinear processing of x, and the estimate, the error becomes orthogonal to all of this processing. So please remember that we are interpreting orthogonality as some kind of a loosely defined independence. Okay, so this error is loosely defined. If it is Gaussian, it's exactly, of course, but now it's like orthogonality says that this error is uncorrelated with this any processing of x, or from the geometric terms, now there is error vector orthogonal to all processing outputs of x. So by processing x any further, I cannot create any dependence for the error. So meaning that I cannot do anything better than that. So this is very remarkable, but this is what we have proved also. Now over here, g of x is arbitrary function. My arbitrary function is this function right now. It's equal to 0. Okay, without doing any operation. So now I end up with this expected value of y square minus expected value of, so what was this? 1 over 2 signum x and y. Okay. So right now this is over y. So can I find the density of y? Let me put the density of y over here. Because it's very easy. So what's the density of y? Y is a random variable between 1 and minus 1. As you see, y is in between x and y. So this is 1 and minus 1. And it's just flat. Okay. So y is, I can say, uniform in minus 1 and y. Okay. Y is such a density. Similarly, x is also like that. Marginal density of x is uniform in x 1 and 1. Okay. So what is this? Expected value of y square. Well, this is sigma y square, because this is 0 mean. And sigma y square is, we have discussed this many times before, if I have a uniform distribution between a and b plus delta, the variance of this, okay, is delta square over 12. Okay. This comes up all the time in signal processing, so I just remember it. Meaning that this is the extent of this uniform distribution. Now the extent is over here 2. Then this is 2 square over 12. Let me write 4 over 12. Okay. This is 4 over 12. Okay, half of the problem is solved. So if I can calculate this, I am done. So this is what? 1 over 2, move this out, expected value of signum x, y, xy. So I need to calculate this expectation. So let's do not, think anything, creative. Just apply the definition of expectation. Let's do not do that for now. So I'm integrating over this xy pair over this area. My function is signum x, y of x, fxy, dx, dy. That is it. But over this area, this is equal to 1/2. Okay? Then, let me move this 1/2 over here, 1/2. Then I have two pieces, isn't it? Piece 1 and piece 2. So one of the integrals, 0, 1, 0, 1, signum xy dx dy plus 1/2 minus 1, 0 signum x y dx dy. As you see, nothing creative. I'm just calculating, what the integral result is. So this x is always positive, so this is 1. So as you see, I get a very simple integrand. This is x is negative, is minus 1. Okay. So what is the result of this integral? So this is 0 to 1, integral of x is just 1. 0 to 1, integral of y is y square over 2, so this is 1/2. Okay? Okay. So this is minus 1 to 0, integral of minus 1 is, well, this is just minus 1. Okay? Because it is it. So this is y. Then I have minus 1 to 0 integral of y square y, this y square over 2. Then insert 0 and insert minus 1. I get minus 1/2. So again, for this one, I'm also getting 1/2. Please check that if you wish. Okay. So is it positive or negative? That is the issue. I get 1/2. So how can I see this? So you can see it this way maybe. So integrand is, this part, is always positive when x, y changes in this region. Integrand. Because y is always negative. Then integrand is always positive. Then if you are summing up positive quantities, you get a positive quantity, whatever the case is. Okay? So integrand is minus 1 times y, but y is always negative, as you see. So what do I have? I have too many 1 over 2's. So let me use this. 1 over 4 plus 1 over 4, this is 1/2. Okay. So what is this? This is this integral. So this integral is then 1/2. So I think we are done. So this is 4 over 12 minus 1 over 2 times 1 over 2. This is the final result. Okay. 1 over 2 times 1 over 2. So this is 4 over 12 minus 3 over 12. I have 1 over 12 one more time. 1 over 4 is 3 over 12. I have 1 over 12 again. So we have make use of this orthogonality, as you see, and we end up with the same MSE value. So this orthogonality somehow simplified our life significantly. Okay. But let me think about that orthogonality a little bit more. So what do I mean by a little bit more? Well, let me erase. Let me keep these drawings. I may need them. Then let me erase this part. This calculation part. On orthogonality. So I want to think about this a little bit further in this example. So is it really, uncorrelated? Minimal, optimal estimator's error is uncorrelated with g of x or not? So question, let's check whether this one, error random variable of optimal estimator is uncorrelated with g of x for all g functions or not. Or we are not checking all g functions, but for g of x equal to x to the power k or not. Okay. I cannot check all of these functions because it will be taking lots of time. I don't want to do that. So I just want to check this x to the power k. So let me say answer, or you may say the solution. So I'm writing this error one more time. Y minus 1 over 2 signum x times x to the power k. Okay? So k is an integer. K, let's say positive integer. I am not considering square roots and so on. I may consider them, but for the sake of simplicity. So the question is it really equal to 0? For different case. So I have written this y minus this, g of x is x to the power k. So again, we are doing a very similar calculation. Okay, so let me write this part. So this is y x to the power k minus 1/2 expected value of signum x, x to the power k. So is it equal to 0? That is the question we are trying to answer. So here is one thing, this is good. Signum x times x. First of all, would you agree that signum x times x is absolute value of x? Let's check. If x is positive, 1 times positive, positive. Negative, you get the magnitude of that, or the absolute value of that. If this is power to the k, well, k is an integer, positive integer, I mean, it doesn't do anything, so I get this, x to the power k. Do you agree? So this is a random variable over x, but it would be even better. Can I find, where are the densities? Density of x is this. So can I find the density of, let me write it over here. If I call a z random variable, this, what is z's density? Well, what do I mean by this? X is known to be uniformly distributed in -1 and 1. So what about my magnitude of x? Well, if you think, you know, how can I think this? Let me tell the answer. Maybe you would be agreeing with me immediately. This is uniform in 0 and 1. Well, the reason is, please remember, this is a mapping like this. Z is equal to this. So x is -1 and 1. X is distributed over here. Now, if you are checking for a z value around this, we have studied this before. Now you are calculating this probability and this probability. And whatever you do, this probability and this probability, everywhere it's uniformly distributed one more time. Okay? Just with this mental picture, you can sense that this is uniformly distributed. Then once it is uniformly distributed, range of z is, well, 0 to 1, because, you know, x is -1 to 1. Then uniformly distributed is 0, 1, you are done. Then, okay, this is equal to expected value of, let me write another color, with another color. This is expected value of z, which is uniform 0, 1, z to the power k then, where z is magnitude of this. So it gets even easier, as you see. So uniformly distributed, then I get my result immediately, because this is 0, 1, z to the power k, f z of z dz. This is just 1, uniformly distributed in 0, 1. So I get 1 over k plus 1 for this part. Okay? Okay, now I should try to calculate this part. So how can I calculate that? Again, let's, you know, apply, you know, usual xy element of a. So 0, 1, or sorry, not right now, it's element of a. I have y, x to the power k, f, it's just 1 over 2, isn't it? 1 over 2 dx dy. Okay. So this is equal to y x to the power k dx dy plus -1 -1 0 y x to the power k dx dy. Okay. Again, we have an easy integral, because x to the power k is, I have 1 over k plus 1. If I integrate with respect to x, move this y's out, then integral over y is just 1. No, not 1, sorry, 1 over 2. Okay. Plus, if you check this, you get again the same result. 1 over k plus 1 times 1 over 2. Okay. Is this correct? X to the power k plus 1 divided by k plus 1, 0 minus 1. So I get that. Okay. And -1, 0, I have this. Okay, so what do I have? Now this is 1 over 2 z to the k plus 1. There is a 1 over 2 factor over here. This one, y to the, I forgot this 2 over here then. Because there is this 2, 1 over 2. So I get 1 over 4. I get 1 over 4 and so on. Okay. Again, is this integrand positive or not? So I'm in the third quadrant. Then y times x, but for this k, I think this is the result. Okay. So this result is 1 over k plus 1 times 1/2. Okay. So my final result is then let me erase this. If I substitute it over here, then this becomes 1 over k plus 1, this part, times 1 over 2, this one, minus 1 over 2 times 1 over k plus 1. So is it equal to 0? Well, indeed it is equal to 0. Okay. So we see that this error is orthogonal to x to the power k for all k's. Now, given this, for example, can I write the following? Expected value of y minus 1 over 2 signum x. This is like sine of x. Is it equal to 0? Well, you can say the following. Sine of x is nothing but x minus power series expansion. Something like this. This is an infinite series. But for every term, there is x to the power k. So all of them are equal to 0 after taking the expectation. So this is true. If you write tangent x, it is true. If you write logarithm of x, whatever, okay, logarithm of magnitude of x and so on, whatever you write, it turns out to be true. And of course, this is not a proof, but this is the illustration. Illustration of it is indeed, uncorrelatedness is the case for this g of x function. Okay. Very good. Okay. So that's all I would like to say. So what's our conclusions? So this is a nonlinear estimator. This is its expression. Okay. So clearly it is nonlinear because a linear estimator will be, a straight line passing from this origin. Okay. It's not like that, obviously. Okay. So this nonlinear estimator is very special. It results in an error of 1 over 12. And there are no other functions that you can, let's say, sketch over here with a smaller result than this. Okay. Okay. So one of these difficulties is calculation of this posterior density. In this example, it wasn't very difficult. But in general, in practice, this is the main difficulty, calculation of this density. So we will be simplifying this a little bit. But before that, I want to discuss the Gaussian case. So let me see. This is our second example. Let's assume y is equal to x plus n. We have a, situation like this. Then x and n are Gaussian distributed random variables. Okay. So the question is, let me put x over here. Or, okay, let me put y over here. Let me put x. So, okay, it's a little strange because we don't use this we use the opposite notation all the time. So I am observing, okay, let's keep this, okay. So observation is x, then variable of interest is y. Okay. So let's say that they are jointly Gaussian distributed, or somehow they are independent, maybe they are jointly Gaussian distributed, let's say. Then the question is, so I have x and y random variables. So this is noise. So this is a noise version of this desired variable of interest. Okay. So I also know that how x and y are distributed. So x and y over here is jointly Gaussian distributed random variables. Okay. So problem starts at this point. So I have this observation. Somehow this is generated, let's say according to this. But I don't want to, estimate, x or so. This is noisy. So I want to estimate this y. Okay. So let's write this joint density of x and y. So let's assume that both of them are zero mean. Assume both x and y are zero mean. Okay. Okay. So I have the following: 1/2 x, y. This is my C matrix, x, y, and so on. So this is my density, as you see. Now, for this question, C is as follows: covariance matrix. So this is, let me say, rho xy, sigma x, sigma y, rho xy, sigma x, sigma y, and this is nothing but, of course, covariance of x and y. Okay, where this is the correlation coefficient. Correlation coefficient. And this is a symmetric matrix. Let me write this a little better. So to calculate this density, I need to take the inverse of this matrix. Let me try to calculate the inverse. So determinant is minus rho xy. Okay. And I have, am I right? Exchange of these two. There is a sign change for the orthogonal terms. Okay, so this is the inverse matrix. So I want to write this expression. Then insert the C inverse matrix over here. Then F density, joint density expression for two random variables which are Gaussian distributed, jointly Gaussian distributed, will be e to the minus 1/2. Then let me be careful. I should write this over here. Let me look at my notes. Okay, so let me write this. Okay, so what's going on? So this is okay. So the x squared term multiplies this term of this inverse matrix. Then you see that x squared times this divided by that. So sigma y squares cancel. So I end up with x square, sigma x square on the denominator times this. Okay. Now xy terms. So xy term multiplies 2 times of this. Okay. So there's a cancellation over here. Let me write this. 2 sigma xy, sigma x, sigma y, x times y. Okay. So this divided by that. Okay. So standard deviations cancel one of those standard deviations. So I'm left with this on the denominator, and this factor is the common factor. Plus, for y square, I have this. Okay. So this is the density. Now, joint density is expressed as you see over here. So the goal is, so what's the problem? So let's calculate the posterior density. Okay. Because this posterior density's mean value, as I have said, median value will be our estimate. So how can I calculate this posterior density? So apply the definition. Okay. So what is this density of x? Density of x is the marginal of this. Marginal of x's, as we have discussed before, is also a Gaussian random variable with 0 mean and variance sigma x square. So let me write that. So there's a constant over here, C2 let's say. There's a constant term, maybe this term is C1. Okay. So function is e to the minus x square over 2 sigma x square. So this is a variation of x, and there's a constant term. So these constant terms are not important because at the end I can normalize this expression. Okay, expression, this is a variable y, and I can find those constants. So how about this one? So this is, let's say, constant 1, e to the minus 1 over 2, 1 minus sigma xy square. Now I want to write this as this. Why? Let me write this and then discuss. Let me write this maybe a bit bigger. Okay, so what's going on? Now this exponent over here is equal to this exponent. This is what I claim. So how can this be? Let's check the y term. So I have y square over here divided by 2. I have something like that, and indeed y square term matches. Okay, how about this xy term? It should be equal to this divided by that. The ratio should be that. If you check the xy term, I have 2 sigma xy times this divided by this. So one of this cancel. 2 sigma xy, sigma x, sigma y is indeed the case. Okay. If you expand this square, the cross term will be, there is a 2 over here. 2 times this part. But this part, this sigma and this second power cancels. I have 2 rho xy divided by sigma y, sigma x. 2 rho, this is this. And if you check this x term is also exactly like this one. Okay. So what do I see? If I take this ratio, then there's a perfect cancellation over here. Okay. By the way, this is called completing to a square. Now this is what I'm expecting. So this is a function of y. So you see that on the exponent there is a quadratic behavior, okay, for y. So this seems to be almost like a distribution of y, which is already, you know, because of this quadratic behavior, when x is fixed, it's almost like a Gaussian. So I'm trying to bring it in the Gaussian form, as you see, by completing to a square. So y minus a constant, okay? Because over here I'm assuming that x will be eventually considered as a constant, not a variable. Y will be the random variable, okay? Then what do I have? I have C1 over C2. Okay, I have something like this. So how about this term? Well, for a constant x, this is already a Gaussian term. And this is then the variance of this Gaussian. Then I don't need to even calculate the C1 over C2 ratio because I know the general form of this Gaussian expression. So this is the variance of this Gaussian distribution. So this is then, and if you of course calculate it, you get C1 over C2 ratio. This is C1 and C2 is 1 over 2 pi sigma x square. If you divide this one by this one, you get this. Okay. And of course, we have already calculated this determinant over here, so you don't have to calculate it again. Okay. That is it. So what do I see? I see that y given x is distributed as n, zero mean. So this is the mean value. It's a Gaussian distribution. It is distributed according to that. So what we see is the following. Conditional density is a Gaussian. So when you play with Gaussian random variables, you end up with Gaussian random variables. You may say things like that. Because if they are jointly Gaussian, if you condition one of them, the other one is, again, conditional density of y given x remains as Gaussian. Okay? So this is interesting. But what is maybe more interesting is, so what's our estimate? If you want to create a, okay, let me keep the problem. Then the minimum MSE estimate for y, let me write y, given observation x is the mean value of the density f y given x, which is, so let me write this. So let me write min.MSE. So this is the minimum MSE, optimal estimate. Min.MSE estimate is this. This is y. I have this. That is that. And furthermore, the estimation error, let me write, the minimum mean square error value is expected value of y minus, of course, the mean of this, expected value, let me call this, y minus y given x, min MSE, square is, which is equal to this one. Okay. Sigma y square 1 minus correlation coefficient 1. This is y minus this. Okay. So how can I see that one? Well, how can I see that one? Well, let me use our orthogonality. Previously we have seen this. So let me briefly write this. So this is equal to expected value of y minus y hat of x, optimal estimator, min.MSE, times y minus expected value of but this is optimal estimator. This part is again 0. So I get expected value of, as you see, we end up with the same result. Expected value of y square times expected value of y hat of x, optimal estimator, min.MSE, times y. Okay. So expected value of y square is, since y is 0 mean, sigma square. I get this term. Okay. How about this one? Well, I should write this optimal estimator from here. And if you do the calculation, if you insert it over here and do the calculation, you get the other term. Okay. So again, this optimality of this estimator comes into the play by the orthogonality principle and simplifies this calculation also. Okay. So I don't need to calculate this 0 essentially. So this, I'm sure that this is equal to 0. So I just write it at the first step. You know, this, strike it out, and then calculate the rest. Okay. So one more time, then this times y should be expected value. So I multiply this quantity by y, take the expected value. You see expected value of x and y is over here. That is covariance of x and y, and if you multiply by this, you immediately get this. Okay. Okay, that is it. Okay, so interesting. So what kind of estimator is this? So let me keep this density. So this is y given x. Note that, let me sketch this estimator. So this is my optimal min.MSE estimator, just a straight line. Because min.MSE, which is equal to this, rho xy, sigma y, sigma x, x. Okay. So the slope is rho xy, sigma y divided by sigma x and 1. Okay. So as you see, a linear estimator. So conclusion number 1, so for jointly Gaussian distributed, now I'm generalizing this a little bit, observations, plural, and desired random variables, meaning that x and y, but if I have many x's and many y's, the estimator, the min.MSE estimator is a, I'm generalizing this to multiple, is a linear estimator. Okay. So you can find the proof of this. For example, if you have 5 observations and you are estimating a random variable, a 6th random variable, then but all of the 6 random variables are jointly Gaussian distributed. So given these 5 observations, what is, so now this is an x vector, let's say. vector with 5 elements, then this density is also a Gaussian distribution. Okay, so for the proof of this, it's not very difficult, but it's a little long, and it's not necessary to do it in the classroom. Okay, so proof is on. I will be putting this on course website. Okay, and I have a document. It's titled is on Gaussian distributions. The title of this document is on Gaussian distributions. Okay, I think this proof is the last proof in this document, on Gaussian distributions document. Now you may have a question: what happens if these, random variables are non-zero mean? Well, I have a very short comment for this. If x and y are jointly Gaussian with non-zero means, then in the earlier derivation replace all x's, then replace x with x minus mu x, y with y minus mu y. So this is expected value of x, obviously, the mean value. Okay, and do the same calculation. So this is the reason that now I have kept this. Now if you do the substitution at the end, because x and y's are generic variables like that, instead of y I'm writing y mu minus y, am I right? Instead of x I'm writing x mu x. So what happens to this one? Then y given x is again Gaussian distributed. So only thing is, now what is the mean value of this? Because there are no other x's or y's in this conditional density. So instead of this one I'm writing x this. So then this is, as you see, let me write. Okay? Because if you do this, you have y minus mu y minus all of these. So the mean of this random variable after conditioning becomes mu y plus this thing. Mu y plus this thing. Okay? So what kind of estimator is this? The mean function. If I sketch this, oh sorry, let me write this variance. I forgot to mention the variance. The variance is the same. 1 minus this. So if I sketch this, mean for this case, now this is a function, but it is something like this. So I'm sketching this function over here. Okay. It's again, slope is the same. Okay. Slope is something like that. And that is it actually. Okay. It's a straight line, but because of this, it's not passing from 0. Okay. So this is passing from when x is equal to this, I have that. Okay, it's all correct. Okay. So what I see is that now the form of this estimator. So this is not linear estimator, but this is what we call an affine estimator. So this estimator is maybe something like this: ax plus b. Okay, so this is the slope, and this is the constant term. So it's in this form, ax plus b, as you see. Okay. So it turns out to be a straight line, but not passing from this origin. Okay, so these are all important observations. So what else? Okay, so that's all for this hour. Then we will continue briefly with more discussions on this after a break. So if I summarize what we have said, in the earlier example we had a nonlinear estimator. For this Gaussian case, if I have jointly Gaussian distributed observations and desired random variables, the optimal estimator in the class of all functions, not linear functions, not all possible functions, becomes a linear function, or what we call an affine function if you allow non-zero means. Okay, and that's all for now. Okay.